Pop quiz, you have 15 seconds. Which reagent gives tert-butyl chloride the fastest? A. Concentrated hydrogen chloride. B. Phosphorus tribromide. C. Thionyl chloride and pyridine. Or D. Sodium bromide. The correct answer is A. Concentrated hydrogen chloride. Tert-butyl alcohol, also called 2-methyl-2-propanol, forms a stable tertiary carbocation. A strong acid, such as hydrogen chloride, protonates the hydroxyl group, allowing water to leave. Then, the chloride ion captures the carbocation via an unimolecular nucleophilic substitution pathway. In this video, you will see how alcohols transform into alkyl halides, into tosylates, which are peritoluene sulfonates, how they dehydrate to alkenes, and how they form esters. We will map mechanisms, choose conditions, work examples, and flag common errors, then carry the logic into a quick application. The hydroxyl group, OH, is a poor leaving group. Chemists either activate it or replace it to build new bonds, turning a generic alcohol into an alkyl halide, into a tosylate, a stronger leaving group, into an alkene by elimination, or into an ester. With that purpose in mind, the substrate class now decides the path. Here is the mental map. Tertiary alcohols favor unimolecular nucleophilic substitution, or SN1, with strong hydrogen halides, such as hydrogen chloride or hydrogen bromide. Primary and many secondary alcohols favor bimolecular nucleophilic substitution, or SN2, using phosphorus tribromide, or thionyl chloride, which avoids unstable carbocations and inverts stereochemistry. With the map in hand, let us build a concrete example. Protonate the hydroxyl with hydrogen chloride, water departs, a tertiary carbocation forms, chloride ion attacks, and the product is tert-butyl chloride. A quick fix to a common error: sodium chloride alone will not work because you need acid to convert the hydroxyl into the leaving group water. With that secured, we can pause to lock the fork in memory. So far, you have the reason we activate the hydroxyl and the rule of thumb for who prefers SN1 versus SN2. Keep that fork in mind as we move to inversion cases. For primary or secondary alcohols, phosphorus tribromide swaps the hydroxyl for bromide by SN2 and gives inversion of configuration. Thionyl chloride, often with pyridine as base, yields alkyl chlorides with inversion as well. Using only acid on primary alcohols can be slow or can trigger rearrangements, so the SN2 route is usually cleaner. One caution before we move on: if you first turn the alcohol into an alkyl halide by SN2 and then do a second SN2 with another nucleophile, you invert twice and end up with net retention. If you want only one inversion at the substitution step, there is a better path. Tosylation solves that. P-toluene sulfonyl chloride with pyridine converts hydroxyl group into tosylate and keeps the configuration at the carbon-oxygen bond. Your nucleophile then attacks once by SN2, giving a single inversion overall and avoiding the double inversion trap. If retention were the goal, 2 SN2 steps could be used on purpose, but when you want clean control with one flip, tosylation is the safer choice. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. When you're done, we'll jump straight into dehydration. Dehydration removes water to form an alkene. With concentrated sulfuric acid and heat, many alcohols undergo elimination, often E1 for secondary and tertiary substrates, giving the Zaitsev product, the more substituted alkene. With a bulky base or tailored conditions, The Hoffman product, the less substituted alkene, can dominate. E2 occurs when a base removes a beta hydrogen as the leaving group departs in one concerted step. Let us see that on a real substrate next. Protonate the tertiary alcohol, lose water, form the carbocation, then a base removes a beta hydrogen to give the more substituted alkene, 2-methyl-2-butene. Keep an eye on rearrangements in E1. Hydride or methyl shifts can appear if a more stable carbocation is possible. While we are on functional group changes, alcohols also step into ester formation. In the Fischer route, a carboxylic acid plus an alcohol with a strong acid and heat gives an ester and water, and removing water drives the equilibrium. In the acid chloride route, an acyl chloride reacts rapidly with an alcohol, often in pyridine, to form the ester under milder conditions. With both routes on the table, let us walk the classic mechanism briefly. Guided steps: activate the carbonyl by protonation. The alcohol attacks, shuffle protons, expel water, then deprotonate to give the ester. With the sequence clear, a few edge cases can save time and points. Reagents are not interchangeable. A primary alcohol with hydrogen bromide, often made with sulfuric acid, can overreact or give side products, so prefer phosphorus tribromide. A tertiary alcohol with thionyl chloride may be sluggish, so prefer hydrogen chloride. SN1 or E1 routes carry a carbocation rearrangement risk. Keep these guardrails in mind as we take on a new case. Convert 2-butanol to 2-bromobutane with inversion. Best pick is phosphorus tribromide, which gives an SN2 backside attack on the secondary alcohol, inverting the stereocenter and avoiding rearrangements. Hydrogen bromide may proceed by SN1 or E1 and scramble configuration. Keep that choice in your pocket as we wrap up. To recap, activate or replace the hydroxyl to make an alkyl halide or a tosylate. Eliminate two alkenes with acid and heat and form esters by Fischer conditions or via acid chlorides. Choose reagents by substrate class and by mechanism. Then check for rearrangement risk. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.